Okay, going to be working 13.2. This is line integrals. And I guess I'll start with number 1. For the line integral of the scalar function y cubed with respect to s, which is arc length, over the curve C, where C is given to us by the parametric equations x equals t cubed, y equals t, and t is bounded between 0 and 2. All right, so all we need to do here is come up with, since we already know the function, the scalar function here, y cubed, we will simply replace that with t, so it'll become t cubed. But ds, remember, is equal to the square root of the derivative of x with respect to t squared plus the derivative of y with respect to t squared. So we're going to need to compute this. Let's go ahead and do it right here. This is square root of derivative of x with respect to t is going to be 3t squared, and the derivative of y with respect to t will just be 1. And so we're going to have 3t squared squared, which will give us 9t to the 4th, plus the derivative of y with respect to t, which is 1 squared, which is 1. And, oh, I'm sorry, I forgot. Out here, we'll have dt. So this will become the integral from, and now over this curve, t is going to be our variable, so t varies from 0 to 2. Y cubed, again, I said that would be this cube, so t cubed. Then ds, which is the square root of 9t to the 4th plus 1 dt. And we just need to evaluate this integral now. And we notice that we can do this with just a basic u substitution. If I let u be equal to 9t to the 4th plus 1, the derivative is going to be 36t cubed dt. I have a t cubed dt, so I'm going to divide both sides by 36, so 1/36 du is equal to t cubed dt. And so this will be replaced with t cubed dt will be replaced with 1/36 du. I'll just show you what the new integral is right here. 1/36 du, and then I have the square root of u, so I'll say u to the 1/2 like that. Now take the antiderivative of this, so add 1 to this, you get 3/2, so 36 times, you have to scale in front, so 1 over 3/2, same as 2/3, u to the 3/2. And then I can clean this up a little bit. Let's see, 2 goes in here. What is that, 18 times? And 18 times 3 is 30, 40, 54. So we should have 1 over 54, u to the 3/2, but u is 9t to the 4th to the 3/2. Okay, now we go in and I'm going to come back over here and say, all right, this is equal to 1/54, 9t to the 4th plus 1 to the 3/2 evaluated, let's see, 0 and 2 here. And plugging in 2, we get what? 2 to the 4th power is 16 times 9. So 1 over 54. Let's see, 16 times 9. That's 90 plus 54, that's 144. So we have 144 plus 1 to the 3/2. That's what we get when we plug in 2. And then when we plug in 0, we get 1 over 54. Let's see, 0 here kills this off, plus 1, so that's just 1. 1 to any power is 1, so we just get 154 times 1. And so we have 154th. I'll go ahead and factor out a 154th from both of those. This is 145 to the 3 halves minus 1. That's our exact answer. Don't see that we're going to be able to simplify that at all. Yeah, we can just leave it like that. That's good. So that's it. That's the value of the line integral. Let's see, let's look at number 3. The 3, we have line integral over the curve C. Here's our scalar function, x, y to the 4th with respect to, again, arc length. And C is the right half of the circle, x squared plus y squared equals 16. So if I graph this, it's the right half of this circle. So we're talking about here, radius of 4 because we've got 16 there. So that's our curve C. And so what I need to do is come up with a parametric equation for C. So C, well, I know how to draw a circle. I can let x be equal to here 4 cosine t. That'll give me a radius of 4. Y will be equal to 4 sine t. And then I need some bounds on t. Well, I want to draw this circle only the right half. So I'm going to try and draw it like this. So what I'll do is I'll start at negative pi over 2 and go to pi over 2. So let's just double check. If I plug in negative pi over 2, cosine of negative pi over 2 is going to be 0 times 4 is 0. So basically when I plug in pi over 2, negative pi over 2 for t, what I get out is x will be 0. And then y, let's see, sine of negative pi over 2. So sine of negative pi over 2 is negative 1 times 4. That gives me negative 4. So I will be at 0, negative 4. So I will start here. And then as I start moving through, I know at pi over 2, this will turn to a positive. So I know I'm going to end up here. And we could just kind of trust that it's going to draw it this way. But let me just check one more point. What about t of 0? We should be here. Let's see. T is 0, cosine of 0 is 1. 1 times 4 is 4, so we get x is 4. And sine of 0 is 0, so we just get 0 there. So yes, we are here. So that should do it for us. So now I'll just come back and think about what I need for this. I need ds. So ds will be equal to the square root of the derivative of x, which is with respect to t, derivative of this squared. So derivative of that, let me just write down underneath here the derivative. I'll just write x prime. This will be negative 4 sine t, and the derivative of y will be 4 cosine t. So if I take the derivative of x and square it, I get 16 sine squared t, plus now the derivative of y, which is this squared, which is 16 cosine squared t dt. And I can factor 16 out of this, and then I'll get sine squared t plus cosine squared t is 1, and then I'll have square root of 16. But the square root of 16 is 4. So ds should be equal to 4 dt. That's nice. So let's go back up now, and let's rewrite this. This will be the integral from negative pi over 2 to pi over 2. X, which is 4 cosine t, okay, times y to the 4th, which is this to the 4th. So 4 sine t to the 4th. And then ds, which is 4 dt. All right, so this will be, see how many 4s do I have? 4, 4, it's 4 squared, and then I have 4 to the 4th. That's 4 to the 6th. I'm going to factor that out as a constant. And then I'm going to write it this way, sine to the 4th t cosine t dt. And I'm kind of hot. Give me a second here. It's hot in this room. Okay, so at this point, I noticed that if I just let u be equal to sine t, the derivative of that is cosine t dt, which I have right here. So this is just a direct, clean, easy substitution. I'm going to get, let's see, this equals 4 to the 6th. So I'm taking the antiderivative of this. It's going to be this. This is like the u. So I have u to the 4th. The antiderivative of that is going to be 1/5 u to the 5th, but that's sine to the 5th t. And I'm evaluating this from negative pi over 2 to pi over 2. All right, so now let's plug in some values. So let's plug in pi over 2 first. So I get 4 to the 6th times 1/5 times, now sine of pi over 2 is 1, to the 5th power is still 1, so we just get that, times 1, minus, then when we plug in negative pi over 2, sine of negative pi over 2 is negative 1, but then to the 5th is still negative 1, so this is just going to turn into negative 4 to the 6th times 1/5. And I get a negative and negative, which is positive. So I'm basically adding that to itself, so I get 2 of them, right? Let me write it this way. I have 4 to the 6th over 5 plus 4 to the 6th over 5. They have the same denominator. So that's going to be 2 of the 4 to the 6th over 5. And let's see if I want to get the actual answer here. Yeah. No, they don't expand that out. They get it as a decimal, 1638.4. Approximately 1638.4. Like that. All right. That's it for number 3. Let's see what number 5 looks like, if it's worth doing. 5. Yeah, I'll do 5. Why not? So for 5, we have line integral over c. Here's our scalar function, x squared y cubed minus root x. Oh, dy. Okay, that's a little different. Then c is the curve. Y equals root x. And from the point 1, 1 to the point 4, 2. Now, it's kind of important that they tell us it's going from this point to this point, because we saw in class that when you do line integrals, the direction of the path, or the direction you travel along C matters. Now, when you're doing a line integral with respect to arc length, it doesn't matter which direction, you get the same answer. But when you do it with respect to y or with respect to x, your answer will differ by sign depending on which way you go on the path. So we want to make sure we understand where we're headed here. So let me draw this real quick. This is what square root of x looks like, right here. That's y's root x. But we only want to go from 1, 1, so from this point to the point 4, 2. So we're only traveling along that piece right there, C. So to do this, we need to find parametric equations for this. Because y is a function of x, what we always do whenever y is a function of x, we just let x be the t. So the independent variable becomes t, and then the y will just be the function, square root of x, but remember x is t, so it's just root t. And now t is going to be constrained here. Well, t is our x value, so our x values are stuck between 1 and 4 here, so 1 to 4. I also need, in this particular problem, I need dy. So dy is just the derivative of this. And the derivative of that is 1 over 2 root t. And remember that the dy actually comes from the formula for ds, where you go dx dt squared plus dy dt squared, and we're saying that that's 0. And so you get dy dt squared square root. So that's why it's just dy. So we don't have to square it. All right, let's do this. We've got the line integral. We're going to go from 1 to 4. And x squared, which is this squared, so t squared, times y cubed. Now remember, this is y. I can write that as t to the half. Right, so I'm going to cube it, so it's going to become t to the 3 halves minus the square root of x, which is this square root of t, and then dy, which we said right here is 1 over 2 root t dt. I should have written over here. Well, this is fine, but really what that is, dy dt equals 1 over 2 root t, and you just bring the dt to the other side. Okay, now that I see this, I think what I'll do is I'm going to rewrite this. This right here, t to the 3 halves, is the same as, how can I write this? Yeah, this is t to the half cubed. That's what I did. That was square root of t cubed, which is square root of t times root t times root t, and those two together are t. So I'm going to rewrite this as root t times t. The reason I'm doing that is because I'm going to distribute this through here, and the root t's are going to cancel. So let's distribute here and here. We'll get integral, we can go 1 to 4. When I do this to this root t and that root t cancel. So all I'm left with is a t cubed over 2. So I'll write 1/2 t cubed. And then when I go here to here, the roots cancel. I just get minus 1/2 dt. And this, I can pull a 1/2 out of everything and be left with t cubed minus 1 dt. And this is 1/2, all right, times antiderivative here, 1/4 t to the 4th. Antiderivative here is t, 1 to 4, and then plug in. So let's see here, here's number 5. Let me just tell you what the answer is, 243 over 8. So I'm not going to go through that work. All right, let's look at number 7. Maybe we'll look at number 7. I guess I'll do 7. So for 7, I have line integral over c of x plus 2y dx plus x squared dy, where c consists of the line segments that go from 0, 0 to 2, 1. And then from 2, 1 back to 3, 0. So I'm going to say this is C1 and this is C2. I'm going to have to break this up into 2 different pieces. Yeah, so let's define these 2 curves, curves. Remember, this is 0, 0, this is 2, 1, and this is the point 3, 0. So if I'm going to define C1, it's going to be a line segment. So I'm going to define it to be with this vector function we call R1 of t. And it's going to connect this point to this point. So I'm going to start at 0, 0. And then t, and then the direction vector that goes from here to here, which is just 2, 1. We did this in class, so I'm assuming you're okay with that. Making sure that shows up on camera. Yeah. All right, and then that's just R1 of t is, add those together, you should just get 2t and then t. So if you want to convert this to parametric, I have an x and a y. I'll call it x1, y1 so we don't confuse it with the C2. This is 2t and this is t. Now, to get C2, I'm going to call R2 of t. We're going to start at 2, 1, and we're going to go to, that's t, this point. So the vector going from here to here is going to be the vector 1, negative 1. And then we put those 2 together. This is going to be 2 plus t, and then 1 minus t. So the x and the y are going to be 2 plus t and 1 minus t. All right, so those are the parametric equations for the 2 curves. And what I need to do here is realize that this is actually going to need to be written as 2 different integrals. This is going to be integral over C1 of x plus 2y dx, and then this part over C1. So I'm going to say plus over C1 x squared dy. So that's just rewriting the notation. This really means 2 integrals. Then I'm going to say plus, now I'm going to go over C2 of that, x plus 2y dx plus over C2 of this one, which is x squared dy. All right. So remember, this notation means integral, integral. But then, so that's this. But then I need to go over, C is actually 2 curves, so this is the first curve, and then add the next one. All right, now converting. So I'm going to go over C1 right now. And because I'm going to integrate over C1, I'm going to use these 2 right there. So this will become, oh, you know what? I forgot to put the restrictions on t. On both of these, t is between 0 and 1. And that's just because of the way that we have learned how to draw line segments. T will always vary between 0 and 1. All right, so this integral will go from 0 to 1. It'll be the x, which is 2t, plus 2 times y, but y is t, so 2t again. And then dx, which is the derivative of the x, which is just 2 dt. All right, then we have plus, next integral, still going over C1, so 0 to 1, x squared, which is this squared, which is 4t squared, times, this time derivative of y, which is derivative of t, which is just 1 dt. Plus, now we're going to go over, I wish I had another color, but I don't. We're going to go over C2, so we're going to be looking at these 2 now. So we've got plus, this one right here goes from 0 to 1 also. X, which is, in this case, 2 plus t, plus 2 times y, which is 2 times this, which is going to be 2 minus 2t. And then times dx, which is derivative of this with respect to t, which is just 1 dt. And I have one more integral to squeeze in here. Plus integral from 0 to 1, x squared, which is going to be this squared. So 2 plus t squared. And then dy, so the derivative of y is, look, negative 1. Be careful here. So this is going to be negative 1 dt. All right. Now, notice all of the integrals go from 0 to 1. So I'm going to turn this all into one big integral, and they're all with respect to t. Let me clean them up first. This right here, if I put that together, pass the 2 through, I get, well, okay, let's do it this way. This right here is 4t, then times 2 is 8t. So I've got 8t here. Here I've got 4t squared, so plus 4t squared. Here, let's see what I've got here. 2 plus 2, that's 4. T minus 2t, it's minus t. So 4 minus t, so plus 4 minus t. And then here, when I square that, I get 4 plus 4t plus t squared. But then I make it all negative. So minus 4 minus 4t minus t squared. That's all my t's now in one big integral dt. And I should be able to clean that up. Let's see, let's count my t squareds first. How many t squareds do I have? I've got 4t squared, take away 1t squared, that leaves me with 3t squared. How many t's do I have? 8 t's, take away a t at 7 t's, take away 4 more, we get 3t. And then 4, take away 4 is gone. So that's it. So this is going to be t cubed plus 3 halves t squared, 0 to 1. So plug in 0, it's all gone. So I just have to plug in 1 here. 1 plus 3 halves, which is 5 halves. See if that looks right. Yeah. Okay. Good to go. Good to go. Okay, let's look at number 9. See how I'm doing on time. I've got time. X, y, z ds, where c is given with the parametric equations. X is 2 sine t, y is t, z is negative 2 cosine t, and t is between 0 and pi. All right, so for this problem, notice this is the first one that we've done so far, where our scalar function in here is a function of 3 variables instead of 2. Our parametric curve has 3 equations. Our curve has 3 parametric equations, so this is a 3-dimensional curve, and it's given to us, which is nice. We don't have to generate the curve ourselves. So let's do this. Let's figure out what we need. We know what x is, we know what y is, we know what z is. We can convert all those over. ds is really the big piece right here. So we're going to need to do ds, which is going to be the square root, and I'm going to write it this way. It's the derivative of x squared plus the derivative of y squared plus the derivative of z squared. So dx dt squared, dy dt squared, dz dt squared. So I'm going to need these derivatives, so I'll get them right here. My derivatives here, x, dt, sorry, out here at the end. X prime is going to be 2 cosine t, y prime is 1, and z prime is positive 2 sine t, sine t. So when I take these and square them, for me, my ds is going to be here, square root of x prime, this squared, so 4 cosine squared t, y prime squared, which is just plus 1, plus 2 sine t squared, which is 4 sine squared t, dt. And then I see that I can put this one and this one together, factor a 4 out. Cosine squared t plus sine squared t will be 1, so I'm going to have a 4 plus a 1, that's 5, so this is just root 5. So all this ds is just root 5 dt. Let's see what this is all about. Give me just a second here. So this integral is going to turn into 0 to pi, x, which is 2 sine t, times y, which is t, times z, which is negative 2 cosine t, times ds, which is root 5 dt. And, oh, I see something. I see something. All right, integral 0 to pi. How about we do this? I wonder if I should pull the negative 2s, or the negative 2 and the 2 out, make it a negative 4 or not. Pull the root 5 out. Let's just do it. Let's just pull all the constants out. Negative 4 root 5. And what we're left with is sine t, cosine t, and then a t in front of all that, like that. Which, this is why I was curious if we should pull that out. This is almost a double angle formula. So let's try something here. Let me rewrite. So I'm going to push a 2 back in. Negative 2 root 5, integral 0 to pi. I've got t times 2 sine t cosine t dt. And now this is sine 2t. And so I have negative 2 root 5 integral 0 to pi of t sine 2t dt. And to integrate that, I think we're going to probably need integration by parts. Let's see how this goes. Let me make a table here. U is t. dv will be sine 2t dt, and then the derivative of u with respect to t is going to be just 1 dt, so just dt, and the antiderivative of this will be negative 1/2 cosine 2t. So check it for yourself. The derivative of this is this. So I can do integration by parts, and so this right here will become negative 1/2 t cosine 2t. So I'm doing, the formula is u times v, so those two, minus the integral of v du. And I notice I have a negative 1/2, which I'm going to pop out here, and that'll come out and make that a positive 1/2. integral, and then all I'm left with is the cosine 2t, like that, dt. And that's negative 1/2 t cosine 2t. The antiderivative of this actually is 1/2 sine 2t, and I already had the 1/2 here, so I think we're just going to have 1/2. Well, let's see here. 1/4 sine 2t. So check that. If I take derivative of sine of 2t, I get cosine of 2t times derivative of what's inside, which is 2. That hits that, I get the 1/2. So I'm good. I am good. All right. That's the antiderivative. Now I still have this in front of it, and I have to evaluate it. So we have that this is equal to negative 2 root 5, it's this, times this, which is negative 1/2. So this negative 2, and that negative cancels. So really, I could just say that that's all just root 5. How about that? Root 5. Okay, t. No, it's all that. Let me be safe here. Hold on. Negative 2 root 5 times all of this. Negative 1/2 t cosine 2t plus 1/4 sine 2t evaluated from 0 to pi. And now I could pull out a negative 1/2, but I'll just leave it. Let's plug in pi. Negative 2 root 5 times, if I plug in pi here, cosine of 2 pi is 1, right? So this turns into a 1, but then times t, which is pi. So I get negative 1/2 pi. Sine of 2 pi is 0, so all that's gone. So that's all I have when I plug in pi, minus negative 2 root 5. Then cosine of 0, right? Cosine of 0 is 1, but then times 0, it's gone. And then sine of 0 is 0. So this is all 0. It's all gone. This whole thing is gone. And so we should just get, let's see, negative and negative is positive. The halves cancel. Get root 5 times pi. Interesting. Nice. I'm going to let you try and handle 11 and 13. I think on 11 it's pretty straightforward. You're gonna have a basic U sub on that. On 13, it's also a basic U sub, so those work out pretty nice. All right, let's go and do number 19 now. For 19, we're asked to evaluate the line integral, but this time we've got a vector field, f dot dr, all right, where f is given to us as a function of two variables, so it's two-dimensional vector field, and it's x, y, I hat plus 3y squared j hat, and they give us that r of t is 11 t to the 4th I hat plus t cubed j hat, and they tell us t is between 0 and 1. Okay. Let me get some stuff in order here first. I'm going to rewrite f the way I did in class. F is going to be, I'm going to write it as a vector. So it's I and j, those are your components. So x, y 3y squared. R of t is, again, two components, 11t to the fourth t cubed. And then, of course, t is between 0 and 1. So what is f, the vector field f dot dr? Well, we saw in class that there was a couple of formulas for this, but we're going to use the one where we have probably this one. It's going to be the integral from a to b of f dotted with the derivative of the r function dt, like that. So I need to dot these two together, but I actually need to, hold on, I left out something. It's f with the vector function, the curve plugged in, dotted with the derivative of the curve dt. So we know the limits of integration here because we're going with respect to t. That's going to be 0 to 1. All right, we need to take the f and we need to plug in our curve. So that means take this vector field, f, plug in the curve to it, which means we're going to get a vector. I take the x times the y. So I look to my curve. Here's the x, here's the y. I'm going to multiply the two together. So that gives me 11t to the 7th. Then this next component is going to be 3 times y squared. So I'm going to take 3 and then square the y. Squaring that, I get t to the 6th. That's the first part of this. Dot that with the derivative of r. So the derivative of r, I'll write it down right here. It's component by component differentiation. So 44t cubed 3t squared. So 44t cubed 3t squared dt. So I just need to dot those two together. Dot products are pretty clean. $440, $484. I believe we get 484 there. So I'm going to multiply these two together. And remember, with dot products, you're just adding. You add after you multiply the components. You add these things together. So 484 t to the 7th times t cubed is t to the 10th plus 3 is 9 t to the 8th dt. The answer should come out to be 45. I won't do the rest of that. All right, next one. Got about 10 more minutes. Let me do I think the rest of these are pretty clean. I'm not seeing anything crazy. I think you can probably do the rest of those. So they give you everything you need. Okay, I'll do one more. Jeez. I'm not going to be able to get to the word problems, I don't think. Not yet. So they give us a vector field. This time the field has 3 components. It's x, y, and x times y. So x, y, and xy. And then they give us our curve. R of t is cosine t, sine t, t. And they give us that t is between 0 and pi. So I know I'm going to need the derivative. Negative sine t, cosine t, 1. I also know I need to take the vector field and plug the curve into it. So when I plug the curve into it, that means I'm going to replace x with this, y, and then z. So x, that's going to be just cosine t. The y is just going to be sine t. And the z component is going to be x times y, so this times this. So notice that we didn't even use that t, cosine t, sine t. All right. So I'm ready to set up the integral. The integral over c of f dot dr is equal to the integral from 0 to pi of the dot product of this right here, cosine t, sine t, cosine t times sine t, dot that with the derivative right here. So negative sine t, cosine t, and 1 dt. And when you multiply cosine times negative sine t, you get integral 0 to pi. Cosine times this is going to be negative sine t cosine t. This times this, you get positive sine t times cosine t, so those are going to be gone. And then this times this, which gives you another one of those, sine t cosine t dt, gone, gone. You're integrating sine t cosine t dt, which is 1/2 sine squared t, evaluated from 0 to pi. And if you do that evaluation, what number was this, 22? You should get 0. And I still have a little time. All right, next one on 37. I don't know. I mean, I think 37 is pretty straightforward. I think 39, I mean, it's basically just like the problems I just did. They give you F, they give you the R. On 39, the only thing I'll say, let me do 39. I won't do 37, I'll do 39. Or at least I'll set it up. So they give you this field in vector form. It's, let's see, x minus y squared. It's y minus z squared. And z minus x squared. And the path, the particle is moving along a straight line segment that goes from the point 0, 0, 1 to the point 2, 1, 0. So I'm going to come up with a vector curve that'll do this for me. R of t will be equal to, I'm going to start here, so 0, 0, 1 plus t times, and now the vector going from here to here will be 2, 1, negative 1. And if I put those together, I get, let's see, 2t, t, and 1 minus t. So this is your x, your y, your z. I think that's all I need. Oh, and then t varies between, of course, 0 and 1, because I'm drawing a line segment. All right, so I should be able to set this thing up. I'm going to squeeze it in right here. Integral over c, vector field, f dot dr should be equal to the integral from 0 to 1 of f with r plugged in. So here's r. I'm going to plug in for x, y, and z into that. So x, which is 2t minus y squared. This is y squared, so t squared, comma. Y, which we know is t, minus z squared, this time is this squared, so 1 minus t squared. And then z, which we know is 1 minus t minus x squared, but x is 2t squared, you get 4t squared. So that right there represents our vector field along that curve, right? With the curve plugged in. I want to dot that with the derivative of the curve, r prime. So derivative of 2t is 2, the derivative of t is 1, and the derivative of 1 minus t is negative 1. That's a pretty nice dot product to do. So this is going to be integral from 0 to 1. I take this, I multiply it by 2, so I get 4t minus 2t squared. I take this, I multiply it by 1, which is just plus t minus 1 minus t squared. I take this, I multiply it by negative 1, which changes it to minus 1 plus t plus 4t squared dt. And I can clean that up a little bit more. So integral 0 to 1. Let's see, this right here is 1 minus 2t plus t squared, but then there's a negative in front, so minus 1 plus 2t minus t squared. So just remember, that's replacing all of that, okay? So let's look at t squareds. I have negative 2t squared minus t squared, it's negative 3t squared plus 4t squared. So should just get a t squared. And then t's, I have 4t plus t is 5t, 6t, 7t, 8t. So my t's are done. And I forgot this t. There we go. And then as far as numbers are concerned, minus 1 is minus 2 dt. What number was this? 39? The answer to that is 7/3. There we go. All right, I'm gonna wait to do the rest on the next video, but that should be enough to get you going.